morning, ladies and gentlemen. Welcome to our joint webinar on quality control for powder metallurgy. My name is Mike Luca. I'm a product manager at ELTRA. I will be your host today. And in the next 1 hour and 30 minutes, we want to give you an overview about quality control for powders, for powder metallurgy, additive manufacturing, and this field of applications. A few things for the organization. Presented will be both presentations by my colleagues. One is Kai Düffels. You can see his picture on the right corner here. He is a product specialist for MRB, Microtrack MRB, sorry. And the second part will be presented by my colleague Kaan Toprak. He is area sales manager for the company ELTRA. You will have, over the whole presentation, you will have the possibility to ask questions. If you work with the app, you will see a question window on the control panel. If you work with your browser, you have on the right upper corner, you have a small bubble where you can click on and ask your questions anytime during the presentation. And now I will hand over to the first part to Kai, and he will present you a basic overview about quality control for powder metallurgy by using particle characterization. So it's your turn, Kai.
Thank you very much, Mike, for introducing me to the audience and for introducing our company, Microtrack MRB. My name is Kai Düffels. I'm a product manager for particle size and particle shape analyzers at Microtrack here in our headquarters in Hahn, Germany. This is close to Düsseldorf, and this is where this broadcast is coming from today. So the first part of this double header webinar on powder metallurgy and quality control is dealing with particle size and particle shape analysis. And you will see this is very essential for determining metal powder quality. So first of all, I would like to give you a brief overview of the products that we at Microtrack MRB can offer. We can offer a complete portfolio of particle size and particle shape analyzers using different technologies. One technology is so-called dynamic image analysis. With dynamic image analysis, we can make pictures of particles, and by analyzing these pictures that are recorded by a camera system, we can determine both size and shape of the powder particles. There are several analyzers that work according to dynamic image analysis. These are analyzers of the ChemSizer series, ChemSizer X2, P4, ChemSizer XL, and as you can see here on this chart, these analyzers cover different size ranges. So when it comes to metal powder, the suitable image analyzer would be the ChemSizer X2, which has a measurement range from 0.8 to about 8 millimeters. 1 millimeter would be wet analysis, dry up to 8 millimeters. And most metal powders are somewhere in the range from 10 micrometers to 100 or maybe a few hundred micrometers. So it's very well in the range of this analyzer, ChemSizer X2, and I will be talking later in this presentation about this ChemSizer X2. The other product line that we have at Microtrack is so-called laser diffraction. Here we have two analyzers, the Sync and the AeroTrack. The AeroTrack is only for aerosols and sprays. The Sync is a very versatile laser diffraction analyzer starting at 10 nanometers and going up to the lower millimeter range. For metal powders, when it comes to metal powders, they also lie very much in the measurement range of the Sync. So this is an alternative method that you can use to qualify your powders. Now, which one is better and which are the advantages of one and the other? I will try to point this out later in my presentation. Most of you will be familiar with another method of particle analysis that is classical or traditional sieve analysis. Sieve analysis is very common, but you are always limited to the number of sieves that you have if you want to get a size distribution. And in many cases, this is not good enough in terms of accuracy and resolution. Also, the sieves have tolerances. So people are looking for more automated, more accurate, and more reproducible and more automated technologies like laser diffraction or image analysis. Finally, here at Microtrack, we have a technology which is called dynamic light scattering. Dynamic light scattering is a method that works very well for nanoparticles. So everything that is in the lower nanometer range, this is where you would use dynamic light scattering. For metal powders, this is not what you would like to use. It can only measure wet, so it's not suitable for metal powders, but very good for nanoparticles. So my presentation today, which will take about 40 to 45 minutes, is divided into 4 chapters. The first chapter is why we measure particle size in the first place and how can that be done. The second part will be about technology laser diffraction and what this technology can do for us. And I will talk about the analyzer that we use for this. That would be the sink. The third part is about how image analysis can be used to improve laser diffraction results, because the sink is not only a pure laser diffraction machine, it has also a built-in camera and can do a little bit of image analysis. And finally, we have the ChemSizer X2, which is a pure dedicated image analysis device. And I will try to explain to you how using an instrument that does only image analysis and is optimized for image analysis can give you even better results, or what's the benefit compared to a laser diffraction, and in what cases you might use the one or the other. So let's see, why do we want to measure particle size or particle size distributions? The size and the size distribution and also the geometry or the morphology of the particles directly affect powder physical properties of the powder, like, for example, flowability, packing density, sintering behavior, and reactivity. Imagine you're using your metal powder in an additive manufacturing process where you have your workpiece built layer by layer. You always have one layer of powder added and then flattened out, and then a new layer is sintered by a laser beam or an electron beam. Then you need a surface and a layer that is smooth and homogeneous and does not have any voids or any particles sticking out, because that would lead to errors and mistakes here in the final workpiece. So it's very important to know flowability, packing density, and also size to judge whether or not a powder is suitable for your process. So what we can get from a particle size analysis is the average size of the particles of the powder, but not only that, but also the size distribution, which is the range from smallest to largest particles, the quantity of oversized particles. By oversized, I mean a small quantity of particles that are much bigger than the rest of the particles, and that would be maybe one big particle sticking out here, and that would be the point where the sintering would not be very efficient. You also want to measure undersized particles, so the dust content, small quantity of particles that are much smaller. And you want to measure particle shape, like roundness, sphericity, aspect ratio. You want to know, are there fused beads, elongated grains, or particles that have satellites, that are small particles sitting on bigger ones. All this would affect the flowability and the behavior of the powder during the process. When you do a particle size analysis, the outcome of the measurement always looks more or less like this. You get a curve that is somehow S-shaped. This is the so-called cumulative distribution. And if you are not familiar with particle sizing, this might be a bit difficult for you to read or to understand. So I will explain now how we get to this type of distribution. Now imagine you do a sieve analysis. Sieve analysis is very comprehensive and easy to understand. You have your powder, you put it on a sieve stack, biggest holes here on the top sieve, smallest holes on the bottom sieve, and then the particles are split into fractions. And you can quantify the fractions by weighing. You always have the lower sieve and the upper sieve, and you have a certain amount in each size class or each fraction. You can convert this to a percentage, and you get the amount in every fraction as some kind of a histogram. And if you add all these bars up, all these fractions up, you get to this cumulative distribution, which is then the result of your particle size analysis, or one way to graphically express the results of your analysis. So you get here this histogram, and you get the cumulative distribution. The cumulative distribution has some advantages because you can directly read so-called percentiles from this distribution. This means for every size, here you get a percentage of particles that is smaller than this size. So at 250 micron, the sum of all smaller fractions would be 36. So 36% are smaller than 250 microns. Or you can see here, we have at the 50% value, or the median, or the D50 would be at 330 microns. And this is how you can characterize your size distribution. Usually you will report the 10 percentile, the 50, and the percentage as 90%. And this is what we would call D10, D50, D90. So this is just for everybody in the audience who maybe is not using particle size analysis on a regular basis. Sometimes you will see distributions that look like this bell-shaped curve here. This is what we call a density distribution, and that's the first derivative of the cumulative distribution. Or the cumulative is the integral of the density distribution. Here you can see the size range and the two curves. If you want to characterize the width of the distribution, you can also see it at the cumulative distribution. The red one here would be a wide distribution, so the size spans over a larger range than for the blue curve. That's a more narrow distribution. And this is also reflected here in the density distribution. The blue one is more narrow, so a narrower span of particle size. And this distribution here goes from 0.1 to 1 millimeter, so it's a wider distribution. If you have a mixture of two different sizes, then we call this a bimodal distribution. So here we have a mixture of small particles and large particles. You have two peaks here in the density distribution and accordingly a step in the cumulative. If you have oversize, like a small percentage of particles that are bigger than the rest, this is reported here in the density distribution as a small side peak and as a outlier here in the cumulative distribution, and this is how you can recognize oversize. So this is just a basic introduction how you can read size distributions. So we can proceed to the second part of my presentation, where we look more at the analyzing techniques, and we will start with laser diffraction. So what is laser diffraction and what can it do for us? Laser diffraction is based on the principle that light is scattered or diffracted by particles. This means if you hit the particles with a laser light, this light beam will be deflected. It will change its direction. And the change of direction, so the angle to which the light is redirected, is characteristic of the particle size. You can see it here in an experiment. This is a cuvette with 10 micrometer particles. It's illuminated by a standard laser pointer. And what you get is here a very characteristic diffraction pattern with rings indicating the angle of redirection of the light. And if you have relatively large particles, then the angle of diffraction is small and you get a ring pattern where the rings are very close to the center. And for smaller particles, these rings move to the outside because you have bigger angles of diffraction. So small particles, large diffraction angle, large particles, small diffraction angles, and also higher intensity. And these are more clear and these are more blurry. The reason why this happens is this particle here is hit by this laser light, which is monochromatic and polarized and coherent. And from the edges of the particles, the light will propagate into space in form of spherical wavefronts. And when these spherical wavefronts meet and interact, there is either constructive or destructive interference, and this leads to this very characteristic ring pattern. When you take a closer look at how this diffraction pattern is changing with size, you will find that you get these diffraction rings for large particles. My particle size d is much larger than the wavelength of the light. You can use this diffraction theory that I have shown here to evaluate the diffraction pattern. This is the so-called Fraunhofer evaluation or Fraunhofer approximation. When you have smaller particles, like this is the same experiment for 1 micrometer, you see that these diffraction rings somehow disappear and the scattering gets more uniform. You still have more light scattered in forward direction than to the side. So here's a lot in forward direction, not so much to the side, but these rings, they disappear. And to evaluate this type of diffraction pattern or scattering pattern, you need a different mathematical approach, which is called the Mie evaluation, named after a physicist, Gustav Mie, who found this out already in 1910. So for this Mie evaluation, the one disadvantage is you must know the optical parameters of your particles, which is basically the refractive index. So if you have this, you can use Mie theory, and this is valid for particles that are close to the particle size is close to the wavelength of the light or smaller. So most metal powders are here in the Fraunhofer range, so this makes our life easier. What makes our life more difficult is that the one here on top and the example on the bottom, they are monodisperse size distributions, so only 1 micron and only 10 micrometers. In reality, you have different sizes in your sample, in your powder, and then all these diffraction patterns from different sizes will overlap, and that makes the evaluation more challenging. But still, it can be done. Now, when you look at your analyze, if you want to use this knowledge to analyze particle size, the instrument that you have to use looks somehow like this. This is a sketch of the beam path in the microtrack sink. We have one laser here, that's laser 1. We have a second laser and a third laser. These lasers are either red, 780 nanometer wavelength, or blue, 405 nanometer wavelength, depending on the instrument configuration. The sample will be here. This is the sample cell. And then we have 2 detectors, one which we call the on-axis detector and one which we call the off-axis detector. And these detectors collect the scattered and diffracted light from the particles. And by using different incident angles of the laser, we can cover a very wide range of angles from 0.02 degree to 163 degree. So this, if you want to measure backscattered light, you use this laser and this detector. If you want to measure light scattered to the side, you use this laser and this detector, for example. One thing that makes the sink special compared to other laser diffraction analyzers is that we have an additional light source, a stroboscopic light, that illuminates the cell and the particles, and the shadow projections of the particles are recorded by a camera. So this gives us additional image information. Now, all this optics is only one part of the analyzer. Still, we need to feed the sample somehow to the instrument. And this is why we have here a docking station for sample delivery modules. And there are 2 sample delivery modules available, one for wet samples, that would be the flow sink, and one for dry samples, that would be the turbo sink. And these modules can be interchanged very easily just by plugging it in and just then pulling it out and replacing it with the other one. There is no need to connect or disconnect any cables, hoses, or tubes. We will see that later in more detail. First of all, I would like to show you how the wet measurement with the flow sink is working. This is the flow sink, which can be connected to the base analyzer, and this is how it looks on the inside. You have a dispersion tank where you see the liquid level here. So the flow sink is filled with a suitable dispersing liquid. It can be water, it can be alcohol, it can be an organic solvent. And this liquid this carrier fluid is pumped through a glass cell. So here we have a cell with windows on both sides, and then is transferred back into the dispersion tank. It holds up to 200 milliliters. and it's a closed circuit. And this is where you would put your sample. This is where you introduce your particles to the system. There's also an ultrasonic probe. The ultrasonic probe can disperse the particles and help separate particles from each other in case they are sticking together. For the dry measurement with the TurboSync, you put your powder on a moving tray. This tray is moving from left to right. And here we have a nozzle that is connected to a vacuum. So the sample is aspired into this pipe here and then transferred to the dispersion area, where you can use some compressed air to introduce shear forces and to separate the particles from each other. So then you have a well-dispersed sample. The measurement is taking place here, and then the sample is carried out of the system by a vacuum that is connected to the analyzer. So let's take a look at some typical examples for laser diffraction analysis. As I have mentioned before, laser diffraction is a method where you have a very wide range of particle size, from 10 nanometers up to the millimeter range. That is a wider range than any other particle analyzer that you will find. So you use it very often to characterize milling processes. Here you have an experiment where we have milled a calcium phosphate in a Retsch mill. Retsch is a sister company of us that also belongs to Further Scientific, and when they do their milling experiments, they very often use the laser diffraction to see what's the outcome of their grinding. So this was calcium phosphate, and you can see this was the initial sample. This is a cumulative distribution, and when you start the grinding, it gets finer after 1 hour, a little finer after 2 hours, and then from after 3 hours grinding, there's not much change. So this is about the size distribution that you can obtain by using this mixer mill. And here you see the percentiles, D10, 50, D90, you see it gets finer. And after 3 hours, you have a median size of about 300 nanometers. So this is a very typical application for laser diffraction, submicrometer particles, milling experiments. Another big advantage of the laser analysis and these instruments is the great repeatability. Here we have measured a glass bead standards with a size range from 10 micrometers to 100 micrometers 10 times in dry mode, about half gram per analysis, 30 seconds analysis time, so it's relatively quick. And here you see the repeatability. It's really great, and so that's a very fast and very reliable process. And these glass beads, they are very much in the size range that you will also find for your metal powders that you, for example, use in additive manufacturing. So as a summary for laser diffraction, what are the advantages of this technology? You have a very wide measurement range, 10 nanometers to 4 millimeters, larger dynamic range than any other technology. It's relatively fast. You can have 1 minute from sample to sample. Depends a little bit on your application, whether or not you need ultrasonic, whether you measure wet or dry. So about 1 sample per minute. So it's relatively quick. It's very versatile. So you can do wet or dry analysis. You have many options for sample preparation. It's highly automatable. You can use standard operating procedures. You have easy handling, little maintenance effort, and it's very robust and not so susceptible to outside interferences like vibration, temperature change, contamination of the liquids. So all this can be handled by the analyzer and does not affect your results very much. Also, the handling can be done by staff that only received a minimum training. So it's really push the button, add sample, and look at the result. And as we've seen, it's very reproducible and also very accurate. If you want to know more about laser diffraction, read the ISO 13320. There the method is described in great detail, and it also defines the requirements to an instrument in terms of accuracy and reproducibility. So these are the advantages of laser diffraction, but everything that has advantages also has some drawbacks. So what can we not do with laser diffraction? We cannot measure particle shape. All the diffraction signal that we get is always related to a spherical model particle. So we assume that all particles are spheres. That's what I mean by we report an equivalent sphere diameter only. So no length, no width, no aspect ratio, nothing. The resolution for large particles is relatively poor. This is because the angle of diffraction gets smaller for big particles, so it's more difficult to measure, and this is why very naturally the resolution and the accuracy for large particles will go down. It is sometimes difficult to measure mixtures. We will see this in a later example. So trimodal measurements, trimodal or bimodal mixtures, if the two different sizes are close together, it's hard to resolve. And there are limits when it comes to the determination of oversized particles. So why would we still want to use the zinc analyzer? Because the zinc analyzer also has a camera built in and can do image analysis. And all these drawbacks here, what the laser analyzer can do not so well, are the strength of an image analyzer. So let's see how we can use image analysis to improve the laser diffraction results and to get a deeper understanding of our sample. So once again, this is the laser setup, laser 1, 2, 3, red or blue, on-axis detector, off-axis detector, very schematic. Here's our sample cell. And now the zinc also has the stroboscopic light source and a camera that acquires particle images. The camera that we use has 5.2 megapixels and it works with 22 to 60 frames per second. This can be selected by the operator. If you want to focus very much on the image analysis, you can use this enhanced imaging at 60 frames per second. During the measurement, you see a real-time visualization of the particles that flow through your measurement cell. So you see a video, actually, of your particles. And after the measurement, the size and shape data from image analysis are reported as a graph or as a data table. And you can also look at every particle that has been recorded by the camera. More than 30 size and shape parameters can be evaluated, like width, length, equivalent area diameter, circularity, aspect ratio, compactness, sphericity, roundness, convexity, transparency, and many more. You have search and filter options, so you can search for particles that have a special property, so certain size or certain shape, or a combination of size and shape. And the size result can be expressed either on diffraction only, imaging only, or a combination of both, where you can use the image data that is more accurate for large particles, and you can blend this into the diffraction results to get a more accurate overall size distribution. So let's look at some examples. Here we have a polymer powder that has a size range from say about 40 microns to a bit over 100 microns. And this powder has been sieved at 100. So there should be no particles bigger than 100 microns. But in the laser diffraction result, we still see that there are about 6.5% bigger than 100. So how can that be? Why does the laser analyzer report big particles even though this powder has been sieved at 100? You will understand this when you look at the images of the particles. You see here, some of these powder particles are very round, but some are fused beads like this one here, or are satellites like this, or this, or this. So now the laser does not know if it's analyzing width or length. If it gets signal from the length of the particle, it will think it's a big sphere. But in reality, it's just an elongated particle. And when you do the sieving, this particle will squeeze through a 100 micrometer hole, because sieving is orienting the particle on the sieve, and then it will just squeeze itself through the sieve by width, not by length. So this can be seen here. You can make these scatter plots from the image analysis, and every point here on the scattergram represents one particle that was measured by the camera. This is, you can have different properties here on the X and Y axis. This would be length, this would be width. Or the round particles plot on a straight line. And here you have particles that are longer than they are thick. Or you can make a plot with length and aspect ratio. Aspect ratio is width divided by length. And here you see very clearly that all the big particles, all the long particles, like this one here, they all have a low aspect ratio. And there are no particles in the sample that are both big and round. And you can do filtering, so you can filter the perfect spheres and analyze only the perfect spheres, and you can find the defective particles and analyze only the defective particles. So now I come to an example where we can use a similar approach to characterize a metal powder. Here we have measured two steel powders, I think it was steel, samples with very similar size, very similar median. So the red one has a median of 34 micrometers, and the blue curve is a median of 37 micrometers, measured with laser diffraction. So very similar size distribution, and you might say, okay, these powders are very similar, they are the same quality. Well, I can use both. But if you look at the images, you see that the particles of one powder are very round. You see all these nice spheres. And if you plot size and sphericity, they all lie very much at the top. Sphericity is a parameter that tells you how similar is your particle to a circle or a sphere. And the number of 1 would be a perfect sphere. So these are very spherical particles. Now sample number 2, there you find all these satellites, elongated particles, and fused beads. And also the scattergram looks very different. See, here are some that are really good spheres, but very many particles have low sphericity. And this can only be found out by using the image analysis, not with laser diffraction. And this information would not be available to us if we would use a pure laser diffraction analyzer. Now, my final example here for how we use image analysis with laser diffraction is this one. This is a bimodal distribution. It looks like. It looks very much like the example I have shown at the very beginning. So it looks like a mixture of two different sizes. But is this really true? Are these big particles and small particles mixed together? When we look at the images, we see that these are very long, needle-shaped, acicular particles. And what we really see here is that this, what appears to be small particles, is the width of these needles, and the second size here would be the length. Because the laser analyzer does not make any difference between width and length, it just puts both into one and the same distribution. The sample here is a calcium silicate, a wollastonite. It just makes very elongated particles. And if you only had the laser diffraction, you would think, oh, it might be a mixture of two different sizes. But if you look at the images, you see, it's really length and width that is reported here. And you can, with the image analysis, actually get a distribution for the width only, that would be the red curve, and for the length only, that would be here the green curve. And if I would take this laser result and plot it here, it would, in the image result, it would be somewhere between these two. Here on the table, you have the percentiles, D10, 50, 90. You see here the laser diffraction spans over a very wide range, and the image result is more narrow because here we can really discriminate between width and length. So this is how image analysis can make our laser diffraction analyzer better, and we get a better understanding of the sample. So by combining diffraction with image analysis, the operator gets additional information. Now we still have analyzers here at Microtrack MRB that do only imaging. So why would we want to use this? Is there anything that the ChemSizer X2 that has no laser diffraction but only imaging? Is there something that this ChemSizer X2 can do even better? Let's find out. So what are the benefits of a dedicated image analysis device such as the ChemSizer X2? Let's see how the ChemSizer X2 is built. For the ChemSizer X2, we have a sample flow, a flow of particles. It can be in an airflow, it can be a dry powder, or it can be a suspension. And these particles are illuminated by two light sources that actually have different wavelengths. And the shadow projections of these particles are recorded by two cameras. These two cameras have different magnifications and different field of view. We have a basic camera with lower magnification, but larger field of view, and a zoom camera with very high magnification, but a smaller field of view. And the zoom camera is the specialist for fine particles, and the basic camera is the specialist for big particles. And they are both active simultaneously and contribute to the result. And this is optimized for the large and for the small particles. The zoom camera is optimized, and they work together to give one size distribution. Now, as I have mentioned before, you can use the ChemSizer X2 as well in a wet mode, which we'll call X-Flow, or in a dry mode, which we call X-Dry. This is how the circulation looks like for the wet mode. It's very similar to the sink. The tank is a bit larger, and you have a glass cell through which the sample is moving. Or you can do dry analysis. Dry analysis is much more common with the ChemSizer than wet. You have your sample here on a vibrating feed chute. The particles drop into this funnel here, are captured by an airflow, which is generated by compressed air, which is connected to the device. The particles are accelerated through a nozzle and separated from each other, and then they are measured here by the two cameras. So the particles can be quite fast here, about 20 to 40 meters per second. So you need cameras with a very high acquisition rate and short exposure time. And the ChemSizer X2 records more than 300 images per second. And there you also already see the difference to the sink. The sink has a maximum of 60 images per second. So here we get much more image data in a shorter period of time. Now let's see how this affects the result. First of all, I would like to talk about oversize detection. In this example, we have a sample which is with spherical particles that are all smaller than 75 micrometers. To this sample, we have added 1 volume percent of particles that are larger than 125 micrometers, so 1% oversize. You can create these types of sample very easily by just using appropriate sieves. Now, when you do diffraction only, you do not find the oversize. This is a sink result with only diffraction. So no particles bigger than 125. 100% are smaller. When you use the sink with the combination of diffraction and imaging, then you find these big particles. You can see them on the images, and they are also represented here in the result rather accurately. 0.7%, 1% have been in there, but you can find them, which you cannot do with diffraction only. So what with the ChemSizer? The ChemSizer is even more sensitive to oversize than the sink, even with the camera. And this is an experiment that was made by one of our customers. They measure metal powders, and they had this distribution of the metal powder. Then they took some oversize, put it on a balance. You see here only a very few grains of oversize. And then they measure with the ChemSizer. This is an example image. You see all the fine particles here, and here's the one bad guy, the oversize. And when they measure this, they can measure 1% oversize with no problem. They can measure 0.2%, 0.1%, 0.05%, and so on. So this is the cumulative distribution here. And when you look at the table, they are able to detect even 0.005% of oversized particles that they have added to their powder very accurately with the ChemSizer. And this is much higher sensitivity than you can get with any other analyzer, including the Sync. The Sync is already good thanks to the camera, but the ChemSizer can get even better, even more sensitive. Now, when we analyze mixtures, we can do a similar test with a powder of spherical particles, maybe a metal powder, where we produce a trimodal mixture, so 3 different sizes. We can also do this by sieving. We take everything that passes through 45 micrometer, then we have the fraction 75 to 90 micrometer, and the fraction larger than 125. So we should have a distribution with 3 maxima. When you do diffraction only, you get only 2. So the third one is missing. When you use the combination in the Sync, combination of diffraction and imaging, there you see a little third signal in between coming up, yeah, but it's not very well separate. When you use imaging only in the Sync, yeah, you get the 3 different sizes, and they are very well separate. But the mixing ratio is close but not perfect. So it should be 33, it should be 66 here, to get the right mixing ratio. And here again, the ChemSizer X2, which does image analysis only with a higher acquisition rate of particles, and which can look at larger sample quantity, which is also an advantage, so more particles, and then your result also gets more accurate. So you can see the 3 signals here, even slightly inhomogeneous distribution here, and you can get the correct mixing ratio, 1/3, 1/3, 1/3. Surprisingly, when you look at the percentiles, D10, D50, D90, the combination technique, the imaging only for the Sync, and the ChemSizer X2, they are not so far apart, because these individual sizes can be measured very accurately. So the small particles are around 40, the other ones are about 80, and the other ones have a average of about 180. Only the diffraction only result is a little bit away from the other ones. So as a summary of these 2 techniques, we have image evaluation with the ChemSizer and also with the Sync, and we have diffraction or scattering methods. The fundamental difference between these 2 technologies is that with image analysis, we are looking at individual particles. Every particle on the image is one signal, one measurement value. With diffraction method, you are always looking at an ensemble of particles or a collective of particles. So the pattern that you see is generated by many particles of different size at the same time. And you need some mathematical assumptions to and theories to recalculate to a size distribution. So here every particle is evaluated, every detected particle is evaluated. This gives us a very high resolution for size, a high sensitivity for oversize and undersize. We can also reasonably calculate number-based distributions, not only volume-based distributions, but also number-based. We can directly measure particle shape. We can use different size definitions like width or length. The disadvantage is that the measurement range is a little bit limited, so we cannot measure sub-micrometer particles. The measurement time is slightly longer than for laser diffraction alone. And as I've mentioned before, no particles smaller than 1 micrometer. For the diffraction methods, the measurement signal is generated simultaneously by all particles. It's a superposition of the signal of many particles. Advantage is we have a wider dynamic range. It's very fast, easy, and reproducible. You have very many areas of application. Laser diffraction is the de facto standard for quality control in many industries, but resolution is limited. You cannot measure number or concentration, and also no number-based distributions or reasonable number-based distributions. You do not get particle shape, and you have a lower sensitivity for oversize and undersize than you have with image analysis. So both the Sync and the ChemSizer X2 provide excellent size and shape analysis for metal powders. Both instruments are successfully used for quality control and also in R&D departments. So we have Sync customers and ChemSizer X2 customers in the metal powder industry. And so both instruments are suitable for that. It depends a little bit on where you want to put your focus on. Okay, laser diffraction, wide measurement range, great flexibility. For metal powders, the Sync is usually operated in wet mode. The imaging option makes the Sync superior to any other laser analyzer, so it can do more for you than only laser diffraction. The ChemSizer X2 fully exploits the advantages of image analysis in terms of sensitivity and resolution. And the ChemSizer X2 provides most accurate sieve correlation. So because we can measure so many particles and we can measure the width of the particle very well, if you need to match sieve results, this is the better instrument. Usually we run ChemSizer X2 in dry mode when we analyze metal powders, so we can analyze large sample quantity, like several grams of powder, for meaningful results. It just gives you a bigger databases than using smaller quantity. So I hope I could give you some guidance to what technology and what analyzer might be the best choice for you. I will be available in the chat during the upcoming ELTRA presentation. Thank you for listening, and this concludes my part, and I will now hand over to my colleague Kaan Toprak. We need about a minute or two to change presenter, so please stay tuned in, and then Kaan will continue.
Okay, hello everybody. I hope you can hear me well, but my colleagues say, okay, sound is good. So thank you very much for participating today in our mutual webinar together with the colleagues of Microtech MRB. I'm very excited to be here and to have the chance to talk to you and tell you about quality control using elemental analysis and powder metallurgy. So my name is Kaan. I'm sales manager at ELTRA. And with me today is Mike, our host and product manager, who is also working on the chat. Any question, you can put it in the chat box. Only Mike will be able to read it, not the many attendees today. So you can ask anything you like. And in case that we cannot answer directly, immediately, we will do it, of course, the latest after this webinar and get back to you with all your questions. So, please let me briefly allow to introduce ourselves as a company. ELTRA this year turns 40. That's still younger than I am, but we are very happy that we have reached this age, and only thanks to you, our customers, we could make it that long, and we are really happy to provide you with solutions, elemental analyzers for such a long time. We are located in Germany, in Hahn. It's a small city between the cities of Düsseldorf and Cologne since 40 years. And our portfolio is elemental analyzers mainly for carbon, sulfur, hydrogen, oxygen, and nitrogen, but also a TGA, a thermogravimetric analyzer, and of course, consumables and accelerators to be used with those analyzers. We are located right here, and the weather is not as excellent as this is in the picture. We have a little bit rain, sky is gray, and we are located here in this tract of the building, a little bit more to the back side, and happy to talk to you from here. Once this situation is changing and traveling is allowed again, all of us are happy to welcome you in our facilities, in our demonstration laboratories, which are here. And there you can test all our analyzers, Microtech MRB, as well as the ELTRA instruments in person in our showrooms. So, additive manufacturing. Additive manufacturing with metal powders is following usually the procedure you have seen in the middle column, starting with the powder production, powder preparation, shaping, printing, followed this. The printing is the real 3D printing, the manufacturing step, you can say, followed by a heat treatment before you get the final product. Where is elemental analysis advisable? First of all, of course, in the powder production, because powders are controlled in many terms for their quality. I will give you more information about that later. And here it's strictly important to see what the material is like, which properties does it have. Then, of course, after shaping, after printing, you get a lot of metal which you can recycle for the next analyzers. Producers of 3D printing instruments give certain advices and recommendations how frequently such a metal can be reused, such a powder can be reused, but of course by controlling quality by yourself in terms of elemental contaminations you have there, or in terms of shape and particle size, you might be able to use and recycle those powders more frequently, which is definitely an economical advantage. And of course, very important, you could see if the powder quality you're using there is already good for operation and for printing. That will save you a lot of time if you see it in that step compared to seeing it in the final product. Yeah, after printing, usually you go through a heat treatment and then you receive a final printed product. Together with the printed product, our customers make a second specimen which they analyze separately. So you have one product which you would like to print, for example, let's say a metal part for a metal spare part for anything, and in parallel you can make a pin, a bowl, a small ball, something like that, which you can simply use in the ELTRA analyzer just by dropping it in and analyzing the elemental composition of the specimen for oxygen, nitrogen, hydrogen, and sulfur, whatever you would like to see there to determine the quality. Powder production starts here in the very beginning with an ore. You follow the procedure of metal production until you get your ingot, and from there you start with the atomization to receive your powder, which is finally processed. It is important to validate the powder quality. There are certain parameters which are important for 3D printing to see if the powder you have used is suitable for the 3D printing procedure. First of all, it's a particle morphology. Kai gave us information about that and how you can get information about the particles and the morphology, as well as the particle size distribution with products from Microtrack MRB. Bulk packaging and flow properties as well, and very important, and this is where we come into the game, is the chemical composition. Because even if you have a nice product of nice size, of nice flow properties, of a suitable morphology, still it is extremely important that you don't have contaminations there, that you don't have a composition of the powder there which will not work for either the production or for the final products. The materials which are used in the 3D printing and which the powders that are used also for the quality testing with elemental analyzers are huge. There are many of them. Copper alloys, titanium alloys, molybdenum, stainless steels, tool steels, nickel-based materials like Inconel, aluminum alloys, tungsten carbide, and many more which are not listed here. The carbon, oxygen, nitrogen, and hydrogen content have great impact on those materials. Testing of powders and final products is highly recommended, and actually it's really necessary as a quality statement for your final product you receive. Let me just give you a few examples to show you the impact on the elements in the material. For example, we have, we have steel, and in steel, the carbon content goes from 0.2% up to 1.7%, where you can control the hardness very effectively. So depending for what the steel is used. Is it used for a knife which should be sharpened? Is it used for a syringe? Is it used for whatever you need? You can define the hardness of the steel. You can define the chemical properties of the steel. Is it stainless or not? By controlling those parameters. If you have a very high carbon content, for example, the steel will be brittle. The product is not ductile at all and is very difficult to handle or to work with. If the steel content is too low, the steel is quite soft and cannot be used, for example, for a key or for a knife, which should be also hardenable. In the medium C content between 0.2 and 1.7, by controlling the content of carbon in the steel, you can control the hardness and design a steel according to your demands. And actually, you as operator will not design it, but you will select the powder you need for your product and can test it for the steel components with the ELTRA analyzer. Next step would be the oxygen. Our next slide tells about the oxygen content in the metals. The oxygen contamination effect is quite obvious here because it will mainly allow corrosion of the materials. You can see a picture here. Increasing corrosivity. Corrosivity is something which is not wanted or usually not wanted in metals. It may crack because of oxide inclusions as well, and will be less stable and less durable. It also has an effect on stability. For example, titanium grade 1 has up to 0.18% of oxygen, while grade 3 has 0.35% of oxygen. So controlling the oxygen content in titanium is for titanium producers really important, so they can tell their customers which grade it is and sell it for their purposes specifically. Nitrogen also has an effect on the metals. You can see it here because it causes porosity. In powders, it also means you have a much larger surface in the powder compared to the standard powder with lower nitrogen content. But the other effect is that metal nitrides may be formed during the process of powder production and printing, so they will disturb the homogeneity of the material. So nitrogen contamination during the production and recycling of powders may happen, and it is very important to control the level of nitrogen in your starting product, the powder, and in your final product, the one that is printed after your process. And hydrogen, again, is also quite nasty. It's a very small atom, and diffusible hydrogen is actually only a fast-moving proton in the metal structure. Still, it has an effect, and it may cause cracks. And it happens from time to time that car producers have big campaigns where they warn the customers and take back cars to change certain parts because it shows that there's a too high hydrogen contamination in some kind of material. So this is that you don't want to see in your car or in any carrying part of a plane. And for that reason, hydrogen is important to control, and this is a process which is done very, very frequently for steel and steel production, and also, of course, for titanium. Where do those contaminations entry in your material, in the powders, and of course in your final material? You can say that additive manufacturing is a little bit similar to welding, because metals are added layer by layer, and the ONH contamination, of course, can happen during the melting cooling cycles. Other sources are powder production and the storage of the powders, the powder bed conditioning, and of course, recycling. So recycling before reusing the powders for 3D printing again, check the powders. it makes really sense and will increase the quality of the final products for sure. Okay, after the general introduction of quality management in the 3D printing, I will now focus on the elemental analyzers that ELTRA produces, which are useful for this kind of quality control. Here you see our Elementric ONHP. This analyzer is for oxygen, nitrogen, and hydrogen detection in solid materials such as metals and powders. For those of you who are not too familiar with the technology, I have a few pictures here which shows how simple and fast analysis is. You simply take your sample. Here we have a metal pin, put it on a balance, add the sample in the sample port of the analyzer. Then you place a crucible at a lower place in the analyzer, press start, and the rest will happen automatically. The rest, that is actually that we are heating up the crucible, and then the sample drops into very hot crucible. The metal will melt, oxygen will be released, hydrogen, nitrogen will be released. Oxygen will react with the graphite crucible to CO, subsequently to CO2, and we detect CO2, hydrogen, and nitrogen with gas detectors such as infrared cells or thermal conductivity detectors. The software will show you the result on a screen very, very simply. So the only thing you actually do, or the operator does, is weighing a sample, putting it in the analyzer together with the crucible and pressing start, and the analyzer will melt it, will process it accordingly and give you the results as a graph and as a figure. The analysis time is quite quick, and it's even quicker now with the second generation of the ONHP. It is now taking roughly 120 to 180 seconds. I'm not talking about analysis time, this is much quicker, but I mean the time for one complete cycle. So every 120 seconds, you can make one analysis, which is actually market leading fast. On this slide, you can see the upper part of the analyzer here. This area, this is the sample port. It's a hole, a funnel hole in the analyzer, and the sample is very simply placed there to analyze it. So just drop your pin, just drop here a nickel basket or a capsule, or just drop your granulates into this opening. No much sample preparation is required here. This capsule, also for those who are not too familiar with the technology, would not be a capsulometry measure, but it would be powders, and powders are placed into that capsule before putting it in the analyzer. So very fine powders, of course, are collected there, and you won't have any dust within the analyzer. This is a nickel basket, which is required, for example, for titanium measurement. Nickel additive is one of the recipes that ELTRA recommends in the application notes as well. So whatever you analyze, it may be powders, it may be solid parts, it may be granulates, or it may be such big nickel basket with titanium inside. The sample port is very easy to access, and just throw the sample in, and it will eventually be measured in the graphite crucible. Here, just for your information, we show distribution of different sizes of metals and grains, which can be used directly without any kind of capsule or basket within our analyzer. We use a high amount here, roughly 2 grams. Typically, the sample amount is from 100 milligrams of sample material for titanium up to 2 grams when you are using copper or steel. Totally depends on the customer and what kind of application they want to have and what kind of demands they are. The deviation that we have is quite good here. It is 0.58% for oxygen only, and ppm, not percent, of course not. No, 0.558% deviation for the oxygen. Again, sorry, I totally mistelling them here. The deviation is only 0.5 ppm. Relative deviation is 8% here, and for oxygen, for nitrogen, the deviation is 3.4 ppm, so quite low and absolutely within the ranges which is acceptable usually and certified for these kind of standards. You will find more information about the standard deviation of our instruments in the download package that is provided with this webinar. As mentioned before, the analysis time of the new instrument, the Elementric ONHP version 2, is even faster than it was before. The cycle time, for example, for oxygen and copper is a little bit more than 2 minutes. For hydrogen and titanium, where you have a longer processing, it's less than 3 minutes. And compared to standard times, you save for each analysis roughly 45 seconds to more than a minute. That means for a standard operator who does maybe 30, 40 analyzers every day, they save more than half an hour of time and operation time of the instrument. So it's a big saving of working time. It's a big saving of money and of availability of the instrument for other purposes. 21 minutes is here listed for 10 titanium measurements compared to 32 as it is with standard analyzers. Quite a nice improvement here. Okay, next is the carbon and sulfur analyzers after the ONH analyzers. Here is a picture of our Elementric CSI. On the left side is the CSI as it is. On the right side, it's the same instrument. The picture is a little bit bigger here. The instruments are actually same size, but here you see the autoloader attached to the instrument. Customers with high throughput can select between a 36 or 130 positions autoloader from ELTRA, which will automatically load the analyzer and distribute the samples there. Quite convenient and a lot of time saving. The measurement principle of the CSI is different because while the ONH analyzer was heating it up with inert gas, so the elements were only extracted. Here we have an oxidization of the sample. So you have usually a metal sample, you burn your metal sample, and carbon and sulfur within the samples are burned as well to CO2 and SO2, which are subsequently detected with infrared cells. The procedure itself, however, is very similar and also extremely easy. Again, simply weigh your sample, put it in the analyzer, press start, and you will get your results. The analysis time here is much quicker. It's only 40 to 60 seconds for a cycle, maybe a little bit longer for purging or so, but CS analysis is typically quicker because it needs less time for the complete preparation of the analyzer and cycling, and then ONH analysis is within 1 minute you have your results. Typical powders or metals that are used are, for example, tungsten carbide. Tungsten carbide is a very fine powder and has a very good homogeneity. And during sintering of tungsten carbide, producers have to very regularly check the carbon content. And it's extremely important to get a very accurate result regardless of the relatively high carbon amount. You can see, and we are really happy about that we can get a relative deviation of 0.1% or even lower for tungsten carbide. And when you measure that, and that's actually a really good result and market-leading result, I would say here. So tungsten carbide can accurately be measured. So producers may distinguish between only small changes of carbon content within their sintering processes. For iron and steel, I also have an example here. Typically 500 milligram of sample is used, and measured 10 times. Also the deviation here is 0.4% only for carbon and 1.1% only for sulfur, which is 2 ppm for both elements. So extremely good recovery and repeatability of the results. It means for you guys who use steels for additive manufacturing or use it as a starting material, you can rely on the C content and the S content that you measure there, and also the final product that you receive. You don't have to be afraid that the measurement could be inaccurate or out of range measuring wise, and can be sure that the product you deliver has exactly the carbon content which is the one required by you or your customers. ELTRA analyzers are measuring oxygen, nitrogen, hydrogen, sulfur, and carbon according to important related standards. Today's operators, they approach us and request that we have a method, that we have an analyzer which is compliant to ASTM norms or DIN ISO norms. And the most important here for powder are the ASTM 1019, which is for carbon, sulfur, nitrogen, and oxygen in steel, nickel, and alloys, and ASTM 1409, which is for the determination of oxygen and nitrogen in titanium and titanium alloys by inert gas fusion. My colleagues in the US are also working together with those groups, together with operators and instrument producers, to be very close to the requirements of the market, to be very close to the requests of the operators and customers. So we are delivering exactly the kind of analyzers with the parameters which are required to be ASTM compliant for our customers. You can see it also in our documents where we state the ISO, ASTM, DIN ISO, and other standards where we are compliant to. And in case that you don't find your standard in one of our documents, it doesn't mean that we don't comply to it, but probably it's just not listed here. You can contact us anytime, and my colleagues, our product managers, who are always within those ASTM norms and who check it very regularly, will give you information if and how we comply to the required norm. As I told you, we simply design our analyzers also according to the requirements. You can see it, for example, here. Here's a schematic overview of ASTM E1019 as a norm, how it should be measured. And on the right side, you can see our schematic scheme of the analyzers, and you see the parallels, the carrier gas cleaning, the furnace area, the carbon cells is not in the same structure, in the same way, so we are sure to comply to the requested ASTMs. Besides the analyzers, ELTRA offers also customer service. Also service to those people who are not ELTRA customers yet, but who are interested, who want to be informed, who have questions, or who just need a support what elemental analyzer is and how it can be determined and how it can be helpful in your laboratories. For example, we have brochures and technical infos for additive manufacturing here, but also for our analyzers, where parameters and procedures are described. Further, we have publications on metal analyzers. These are actually nice overall reads about carbon and sulfur determination, about powders and metal parts produced by additive manufacturing. Just worth checking them and to get an overview of the elemental analysis in that field. And don't worry, they are all available in the download which will come together with this webinar. But I guess the probably most important kind of documents that we offer to you are our application notes. The application notes can be considered as a recipe how to measure oxygen in copper. But actually, as you can see here in this overview, it is much more than that. It's not only use 500 milligrams of copper and use graphite crucible. It gives the parameters of the heating. It gives the conditions of the analyzer that could be adjusted. It gives an overview how the sample is prepared and how the calibration is done of the instrument. And also it gives a kind of troubleshooting or instructions how to improve results and how to get better repeatabilities for the measurements. Just in case you're already working with elemental analyzers, it's still worth checking it and to get an overview how to maybe even improve your results a little bit. So this tips and hints is the thing that everybody can need, I guess, while application and settings and procedure, once you have it, you can keep it as it is. Always worth checking those. We have quite a few of them also together with the download package of this webinar. Another service that we are offering is demos and testing. Usually we do demos in our laboratory as well, or in one of the laboratories that ELTRA has worldwide, in the US, in India, in China, in South Korea. So everywhere we or our distributors have online laboratories, but these days we make it more online. So customers follow us on the PCs virtually how we make measurements. We can either use your original samples that you can send us, or we can use some standard samples or samples that we have here to show you how the analyzers operated, how the software is operated. You can have even a little bit hands-on with the software by using TeamViewer. So this is something which is a very nice option to demonstrate the reliability and the ease of use of our instruments. Further, we can do sample testing. So in case you are interested in purchasing an analyzer, but you need to fulfill certain requirements, just send us your samples. We will test them, send you the results together with the report, and you will see that we hopefully comply and meet your requirements as it is. We also give application support for operators who are facing the situation that they have maybe new samples, who are not sure how to deal with them. We will give information about application, how to measure them to get the best possible results. You can also visit us on ELTRA.com to see about the details there and make an appointment with us and contact us there. Also, can contact us these days on LinkedIn. My colleague Mike is quite active there, and also others of my colleagues and distributors worldwide write there, share their experiences, give information about new applications and new instruments. Always worth checking and checking our LinkedIn page. And of course, the easiest would be if you simply follow ELTRA, connect with us, then you will get the information then and when in your timeline. You can contact us by Teams or any kind of other video conference software just for communication, or as I mentioned, for a live demo, or you can use the chat function on ELTRA.com on the homepage. One of us is always there and replying to the customer questions that pop up here. And of course, still the other channels like email, SMS, and phone calls are also available for our customers. So I don't want to leave and say goodbye before giving a very, very small overview of the other kind of instruments ELTRA has. we have CS analyzers, not only for metals, but also for organic and inorganic samples such as coal or woods. We have ONH analyzers for metals, ceramics, and inorganics. And we have a TGA, a thermogravimetric automatic analyzer for moisture, volatiles, and ash determination. So if you are in demand or interested in any information about those analyzers, don't hesitate to let us know. We will be glad to help you. ELTRA is part of the Rare Scientific, such as Microtech MRB is also part of Rare Scientific. We are a group of companies, and you have heard a little bit about Microtech and ELTRA today. I also want to mention our sister companies, ASTM, who is expert in materialography and hardness testing, Carbolite Gero for heat treatment, and Reg, market-leading company for milling and sieving. My name is Khan from ELTRA Elemental Analyzers. My colleagues Mike Luca and Andreas Tyson and I are all available for any kind of comments and question. Just contact us. You can also use the QR codes here to connect with us via LinkedIn. Thank you very much for your time. Thank you very much for the questions or comments you sent us. I see Mike is quite busy with answering, and in case that we cannot answer all of them, we will do so after this webinar and within today, of course. And yeah, thank you for attending, your time and your interest in rather scientific products for the additive manufacturing of powders.
Yeah, thank you, Khan. Thank you all for listening to us during the last 1.5 hours. We are still a little bit available for upcoming questions. So if you have any, just type them in the question window or come back later to us via email. You will receive tomorrow a download package with all relevant information on today's webinar, also the presentations, application notes my colleague mentioned already. Not only from ELTRA, of course, also from Microtech MRB. Yeah, thank you very much. If you have any questions, if you have samples you want to have processed, we have many companies and customers who are working with Microtech MRB laser diffraction or image analysis as well as ELTRA analyzers, because quality control are mostly in the same part of these companies or of your companies. So we are working very close together, and we're receiving also a lot of samples here in-house, which we proceed in the Microtech MRB laboratory, which is next door to our laboratory down here. So feel free to send us also your samples, and we can have an online demonstration, we can process them, send you the information and the results. And now I give you some time to type in your questions. Thank you from my side. Thank you, Khan. Thank you, Kai. And have a nice day or have a nice evening.